Morning, everyone. My name is Spencer Huang. I'm today's speaker. So I maybe we can wait for 1 minute and for other people to join. Anyone hear me okay?
Yep, sounds good.
Okay, and you can see the slides, right?
Yes.
All right. Just want to make sure that there's no problem with the technology. Okay. All right, let's wait for 1 minute and then we can get started this seminar. Yeah, I think we can get started with this CPSI Spotlight seminar to talk about how to create an analytical data set from EHR dataset. This is a CTSI Biostatistics Epidemiology and Research Design seminar. We have three previous seminar lecture from March, and this will be the last one of this special lecture series to learn how to create an analytical data set for EHR data. My name is Spencer Huang. I'm a professor of biostatistics. Just a moment. Yeah. And I'm currently the director of the BIRD function, meaning under the CTSI. We provide several services of statistical support for the CTSI community. So in general, this statistical support is provided through the Zilber School of Public Health, which is I am a faculty under the Biostatistics division. Also, we provide a more comprehensive statistical support through Biostatistics Consulting Service within the Institute of Health and Equity Division of Biostatistics at MCW. We also have the CAPS, the Milwaukee Center for Advancing Population Science within the Department of Medicine at MCW to provide different statistical support. So for the BIRD, we provided support through the mini grant. In general, we provided 4 to 6 hours of statistical support. The type of mini grant proposal that which is likely to be awarded is in the following category. We provide support to discuss and review project and study design. We also help to review data and confirm data analysis plan. We provide a sample size calculation of power analysis. We also provide a short preliminary data analysis, but not comprehensive data analysis related to your specific study design. We also help to review data analysis. Once you're done, we can help discuss the finding and interpret the result. So here is the website you can log in and to seek for this statistical consultation. So if something beyond this service, we would like to refer you to a more comprehensive statistical consulting service for the full statistical service that will include more about the modeling and data management, especially for the electronic medical record, which is very comprehensive, and I will talk more about the complexity of this in today's lecture. Also, we kind of help with the data analysis, and a lot of data analysis is very involved, require a lot of checking and back and forth discussion with the investigator. So this is not a one-time service. Therefore, we will kind of refer investigator or any connection to this type of service to the BCS service MCW. And especially if you have some grant proposal, then I would recommend that you will go to the BCS for this type of service. So for the BCS service, it's a fee for service. For the MCW account, the fact if you ask for faculty or support, it will require about $165 per hour. If you just require the MS statistician to do the data analysis and making table, figure, and so on, the fee is $100 per hour. So you can email here the consultant at mcw.edu. Also, we provide integration contracts. For example, your department can make a contract with the BCS, then your service will be free once the contract is done. So far, we have contracts with several departments, MCW, like surgery, physical medicine, rehabilitation, further pharmacy, and so on. So all the information will be here, and because this lecture will be recorded, so you can come back and look at those information. So in the past 3 months, my colleague has discussed several issues regarding the electron health record preparation and design. So including the observation study using EHR and how we can define the cohorts. And last month, we talked about defining the outcome. So today, I'm going to discuss how to create an analytical data set for EHR data. Okay. So the objective of this presentation was to help you understand the electron health records data structure, and also help you to understand the principles and basics of the data processing, including how to make a reproducibility feasible, and how to make a data transformation, manipulation, and data integration from different files. At the end of this presentation, I will demonstrate the process of creating an analytical data file from the identified cohort data through Trinetics or Honest Broker system. And I hope that some of you may have some experience in working with the electron medical record. So first, before I talk about the data manipulation and integration, I want to point some very important concept regarding how to work on the electron medical record. The first point is about study cohort fidelity. So we have to remember that the query algorithm, meaning to query the data from EHR database, are generally unable to boast 100% accuracy to identify the sought patient phenotype. So therefore, the false positive and false negative are expected. In order to guarantee the fidelity of the study cohort, manually reviewing a random subset of the selected patient can be helpful. Based on the size of the study cohort, I think 5 to 10% of the clinical chart should be reviewed and to ensure that the presence and absence of the exposure of interest. Okay. So this task in general should be accomplished by a clinician or multiple clinicians. And if resources are permitted, 2 clinicians reviewer can be tasked with this role, and their independence result should be compared using a kappa statistic to see how concordant their review result is. Ultimately, the investigators can use the gold standard of manual review to establish through the ROC. This is an area under the ROC curve. So in general, we would like to have like more than 80% ROC curve value that will indicate a good accuracy of the algorithm to identify the patient cohort that you need. And that should be used an absolute minimum of algorithm fidelity. So unfortunately, sometimes the area under this ROC curve can be less than 80%. In that case, a combination of the data visualization to understand what happened to the data and the clinical reasoning say maybe there's something to deal with the ICD-9 or ICD-10 code should be used to better tune the query algorithm to the exposure of interest. So it's very important that we need to double check the data quality before we move to the data manipulation. Now, once you pass that, the next step is do the data preparation. Data is at the core of the all research, as we know. So robust data management practices are very important if studies are to be carried out efficiently and reliably. The same can be said, for example, for the management of the software used to process and analyze data. To ensure good practices, that is very important in place at the beginning of a study, that can result in a significant saving further down the road in terms of the time and effort. As we normally know that it's garbage in, garbage out, and the electronic medical record is pretty noisy and messy. So we need to ensure that the data quality is there. So once we get the data clean and the data analysis downstream will be much easier. Really, that will save you a lot of time. It's a very important concept that we should understand. Now, this topic I will talk about the reproducibility. For any study, investigators and data analysis should ensure that the study are as far as you can reproducible. So by making data and code accessible, we can more easily detect and fix inevitable errors. And also can help each other to learn from our methods and promote better quality research. When practicing reproducible research, the source data should not be modified, and this is a very important part. Sometimes investigators that work on their own. So once they get an electronic medical record, because the massive data they try to clean on their own using Excel. Okay, so they generate a lot of data file. Okay, so you need to make sure that the original data is fixed and freeze and don't modify it anymore, because once you modify it, you won't be able to get back to the raw data. So this is one of the most important concepts I would like to emphasize here. Okay. Then editing the raw data because adding the raw data destroys the certain of the reproducibility. So instead, code is used to process the data so that all of the steps that take an analysis from the source to outcome can be reproduced. This is something I want to mention here, that a lot of people just want to use Excel because of the convenience. However, if you use Excel, you won't be able to remember how you process the data downstream. So once you find some error later on, you won't be able to go back to figure out what I have done before. Okay. So that's why I encourage you guys to work with the analyst to ensure that we have code stored there. So once we find something wrong, we can always go back to check the code to see what's happened that we did before that was wrong. Okay. The code and data should be well documented. Typically, it is to provide a plain text README. So in nowadays, a lot of publication require your code to be publicly available. People normally put it into GitHub, so it's open to all the public. But here, I don't think we need to do that, as so far there's no specific timeline for manipulated data in electronic medical record. So probably you don't need to kind of put into GitHub. However, I really strongly encourage you guys to work with the statistician, that they will always provide a code that you can always track back and use that code to generate the data that they have produced. Now, there's many tools like a Jupyter notebook or Markdown to interweave the code and text that will help you to see how you can reproduce what you had done before. So this is just a snapshot of the Markdown, right? So you can see here, that's the code, right? And in general, if you run the code, and you have the data file in your computer. You just run the code, and then you can generate the file, the image, the pictures, or the result, the table that other statistician has done before. Okay. Now let's talk about the data file and database. Okay. Data can be in general break into two types, either quantitative or qualitative. The quantitative data is data that can be measured, written down with numbers, and manipulated numerically. Quantitative data can be discrete, taking only certain value, for example, like integer 1, 2, 3, or continuous, taking any value, right, like a height, weight, and so on. The number of times a patient is admitted to a hospital is discrete, and while like a patient weight is continuous. Just some example. And what talk about the qualitative data, this is information which cannot be expressed as a number, and is often collected using questionnaires, interview, or from clinician note. Sometimes qualitative data used interchangeably with the term categorical data when there is not a natural ordering of the categories. For example, a patient ethnicity, the data is called nominal. Okay. When the categories can be ordered, and these are called ordinal variable. For example, like a severity of the pain on a scale. So each of those possible values of a categorical variable is commonly referred to as a label. So depends on how many labels it is, right? Data is typically made available through a database or a file which may have been exported from a database, where there are many different kind of databases and data file in use. Relational databases and the common separate value or the CSV file are perhaps the most common. The common separate values CSV file are plain text file, you can see here, and used for storing data in a tabular spreadsheet type structure, where there are no hard or fast rule for structuring tabular data. It is usually considered a good practice to include a header row, as you can see here is a header row, right? To this each variables in a separate column, and to this observation in a row. So now you can see there are several rows here. Each row represents one observation. The CSV format is popular largely because its simplicity and versatility. CSV file can be edited with a text editor, so you can open a CSV file in the text notepad, okay? Or you can load it as a spreadsheet in Excel, okay? So it's pretty convenient. And you can import and process it by most of the data analysis package or software. So often the CSV file and intermediate data format used to hold data that has been extracted from a relational database in preparation for analysis. There are several styles of database in use today, but I think probably the most widely implemented is the relational database. Relational databases can be thought as a collection of tables which are linked through a shared keys like a patient ID. Organizing data across the table can help to maintain data integrity and enable faster analysis and more efficient storage. In the SQL or R TDVerse package, you can perform several data integration through a different functional joins. This joint is not complicated, however, it's beyond the topic of today's presentation. So if you're interested, you can work with the CTSI to learn more about how to use this joint. However, you will require some programming skill. Now, let me talk a little bit about the data preprocessing. Data preprocessing consists of a series of steps to transform the raw data derived from the data extraction, like I mentioned earlier, into a clean and tidy data set prior to the statistical analysis. Research using electron health records often involve the secondary data analysis of the health record that were collected for clinical and building purpose and placed in a study database through this automatic process. Therefore, this database can have many quality control issues, and preprocessing, the goal of preprocessing is try to assess and improving the quality of data to allow for reliable statistical analysis. So in general, that will involve several steps, including the data cleaning and data transformation. And this is the main things I would like to discuss in today's presentation. So the EHR data are usually pretty messy in the sense that they can incomplete, for example, the missing data, and they can be noise like due to the random error or some outlier value that deviated from the expected baseline value. And they can be inconsistent. For example, the patient's age is 21 and the admission service is neonatal intensive care unit. And so this is the inconsistent example. The reason for these are multiple. Missing data can be due to random technical issues with like biomonitors, reliance on human data entry, or because some clinical variables are not consistently collected since EHR data were collected for non-study purposes. Similarly, the noise data can be due to fault or technological limitation of the instrument during data gathering. The noise data and outlier are error and discordant data that may arise from natural variation within the population or process, and the consequences of not screening the data for outlier can be a big issue. So there are several ways to detect the outlier. The most easiest way is through this simple univariate analysis. In this case, the core principle of discovering outlier is to just determine the statistical trial of the underlying distribution, and assuming that either too big or too small value outlier. And sometimes the univariate approach may not be able to detect outlier. In that case, we will try to use the multivariate approach to consider, for example, two variables at a time, and in the data visualization approach that we can see some of the outlier in the figure. Now, the next method I would like to talk about is the IQR method, or the Tukey method. So let me define what's the inner fences. Okay, so for first thing, when you talk about the interquartile range, we're going to know about the 25 percentile of the 75 percentile of the data values. So we define this as the Q1 and Q3 for 25 percentile and 75 percentile. The inner fences are located at a distance of 1.5 IQR, okay, below the Q1 and above the Q3. So IQR is defined as the difference between the Q3 and Q1. Okay, and the outer fences at the distance of 3 times of the IQR below the Q1 and above the Q3. So a value, by definition, between the inner and the outer fences is a possible outlier, and whereas a value falling outside the outer fences is a probable outlier. So the removal of all possible and probable outlier is referred as the IQR method, while the two-key methods only remove the probable outlier as discussed. So as I discussed here, the two-key method is a more stringent method because it will remove a much larger or smaller values from the data set. So let me give you an example of this approach. Here, as you can see, I display two variables in a scatter plot. One is on the x-axis, one is on the y-axis here. Okay, so as you can see here, I make a box plot to know the distribution of both variables. Look at the x-axis right here. Here, this is the Q1, okay, the 25th percentile value, and this is the 75% value. Now, in the middle here, this is the median value. So now from this point to this point, we find that actually there's no outlier. No one's going to exceed this 1.5 IQR. Okay? And here, this is a 1.5 IQR, this range. So if we look at this univariate analysis plot, you don't see any outlier. However, once you look at this multivariate picture right here, you can see sort of this cross points kind of deviate from the majority of data points that could be considered as a potential outlier. So this is the approach that we can aid to identify potential outlier in the data set. Now, next step is about this Z-score method. So the Z-score method actually is to compute the number of standard deviation by which the data varies from the mean. This approach represents a reasonable criterion for the identification of outlier when the data is assumed a normal distribution. Okay. It's a rule of thumb is to consider values Z-score greater than 3 standard deviation as the outlier. And I want to make a note that the method is of limited value for small data set because you won't be able to find any value greater than 3 standard deviation from the mean. Okay. So it's not helpful if you just have a small data set, say sample size is only like 10 or 15 also. When the data is not normal distributed, for example, is skewed to the right, you may want to consider use transformation on the data, like taking the log transformation, and after that you can use the IQR method or the two-key method. Other than those simple methods, a more sophisticated approach can be done through regression modeling approach. Normally, we fit a regression model and look at the residual, okay, the difference between the observed and the fitted value to see how big the residual is. In general, there are some statistical techniques to detect those residuals that can be considered as outlier. And this is a most in-depth approach, and you will need to consult with a statistician if you want to see if there's a potential outlier that should be removed from the data analysis. So at the end, I want to make some caution for the process and the outlier. It's very important to distinguish outlier as a useful and informative, not clear cut, because evaluating the effectiveness of an outlier detection algorithm and comparing the different approach is very complex. Moreover, because the ground truth about outliers is often unavailable, we actually don't know which ones are outlier, and is that due to the coding issue or some error or some other issue. And in certain contexts, outlier may represent extremely valuable information that must not be discarded due to the biological variation rather than the experimental mistake. Okay. So I would highly encourage people to make some plot to visualize the data Especially the data can easily reveal some very high value. Once you observe this high value, it's very important that clinician, research, and the statistician need to talk together to know what's going on with this data point before you decided to remove the data. So it's very important that expert eye must be prevailed right before deleting and correcting the outlier. So there are several other important steps in the data pre-processing that is key to this process that include the data transformation, such as a filter a subset observation based on certain values. And you also want to select certain variables that are relevant to the study. You will find out when you get the electronic medical record from a regional database, it's very likely that you have tons of variables. And you don't need all the variables to import into the data analysis. So one thing is because that can reduce the size of data. Sometimes it's very important to import a very, very large data file into a statistical analysis. Now, sometimes you also need to add new variables that are functions of existing variables. And I will show it in the case study later on. So before I talk about detail, I want to show this case study to help you understand the steps that I have mentioned earlier. I won't be able to tell you all the steps that I discussed here because it's very tedious and time-consuming. We won't be able to finish that within a 1 hour lecture. So I will just talk about some of the steps that we normally and frequently use in the data manipulation processing. So this is a study to deal with the obstructive sleep apnea, OSA, and its impact on risk of cancer. Hello?
Ay, en la trabajación.
Ay, qué horrible. Yo ya terminé por ahí.
Ah, tú terminaste. Oye, terminaste temprano.
No. Mira,
Could everyone mute,
¿Quién está hablando? Yo.
please?
Oh, mira.
Hello? Can anyone mute? Thank you.
Ay, ay, ay.
Okay. So we have some clinical observation knowing that a patient with cancer have impaired sleep and non-standing sleep disturbances cause cancer. So it's possible that the OSA patient have a higher risk of cancer, and we also question if there's a connection between the pre-existing sleep disorders and survival and their response to therapy and recurrence in cancer. So to prepare for this data, actually, this is the data that was used in the CTSI data science computation in the day April. So I just want to use this example to demonstrate how we can pre-process data. So we didn't include all the cancer patients. Instead, we only include patients with the following 8 different type of cancer plus the OSA. So these are all the ICD code that we use to extract the data. So the data cohort is an aggregate data set of 31,536 patients that are not contain an equal distribution of 4 different types of patient. First type is the cancer only, meaning the patient with cancer only, and the patient with OSA only, okay, meaning the OSA but no cancer. A cancer with both cancer, patient with both cancer and sleep apnea, and patient neither have cancer nor the sleep apnea. So now this is all the data that we have. So from the relational database, we extract those data files. The first one is the demographic file, which contains 31,536 patient records. These are the unique patient records. Next one is the biggest file. This is the diagnosis file, which contains more than 34 million records from all those patients. Because you can imagine the patient has multiple visits to the hospital and clinical record, right? Encounter records. That's why it has such a big file. Now you can see with this such big file, how can you get a reasonable data file for the data analysis? That definitely will require a lot of data preprocessing. We also have the data from the NAACC, meaning the North American Association of Central Cancer Registry data that include all the cancer patient information diagnosis. We also have 2 other files, including social information and vital information. All those files are stored in this database. So you can, this is the file. I take a snapshot of a different file. As you can see, this records and all the different variable names from the different file. I highly encourage people to understand the data structure before you move to data preparation and data analysis. So the first step I want you to do is you import data into a statistical software. Sure, sometimes you can open that in an Excel file if the data is not a big. However, for example, the demographic, the diagnosis file is too large to open in Excel file. So in that case, you really need to add data statistics software to import in and look at the data. So once you import the data, you kind of check the number of records and number of variables and type of variables, right? For example, if sex is a categorical variable, and maybe some other variable is a numerical variable, and so on. You also can check its possible missing value from this procedure. And normally you want to know the distribution of the most of the variable of interest for your data analysis. For example, in the demographic variable, you want to see a distribution of a race in your data set. So you just use a simple syntax, you can know the distribution from a different ethnic group. You also know how many patients has died and how many patients still alive, right? If you want to perform survival data analysis, and the simple code can tell you the distribution of these 2 types of patients. Okay. It's very important that from this very simple analysis, you can see how many missing data is, right? If some variable has too many missing data, you won't be able to perform analysis from your interest. So it's very important that you check with the missing data, okay? Unless you have a specific idea how you can work with the statistician to overcome the missing data value through some imputation technique. You may think, well, importing data is a very simple approach. However, it is not. Okay, the data sometimes has very special character. Okay, for example, here it has a dot before this cancer type. So this actually causes the data import to stop at this record. And in this case, you don't know what's going on, and you need to have some experienced data analyst to know. Okay, you go back to data to see why it stopped import data after a certain number of records. Go back to original data, open the file to know what's going on, fix the problem, and you can import data again. And now I mentioned earlier, you can check from each data set how many records you have and how many unique patients you can have, right? Because that you can check the accuracy of data compared to what you have been taught about the data set. So for this data set, we have a very specific aims to address. First, we want to know the cancer patient with OSA, a diagnosis has worse survival than those without the OSA. And the second question is, among the cancer patients, severity of OSA diagnosis is associated with a poor survival. So these are two very specific questions. And based on this question, the following we're going to tell you how we can generate the data. So this is an example of how we can start with the data. We write down all the code with our markdown file. So this is just a snapshot of our markdown file. I want to show the total markdown file. This is the whole entire markdown file. As you can see, there's hundreds of lines of code and so on. So this is not trivial, but it's very important that you keep all the code. Okay. So this is the variable selection step that includes which variable that we want to select from which data file. For example, for the demographic file, we want to extract the sex, birthday, vital status, death date. And for the diagnosis file, we want to extract the diagnostic date and diagnostic code, and so on. So I will tell you why we need to kind of have those variables in order to create some other information for the data analysis. Now let's talk about the data filtering. So we want to keep the record of a patient diagnosed with cancer or the OSA, right? And want to remove record of patient without both cancer and OSA. So this will be done from the diagnosis file. Okay. So after the process, the number of records reduced from 34 million records down to only 1.8 million records. So you can see this substantial reduction in the data file. And from those records, we identified a unique patient down from 30,000 to about 23,000. So actually, we remove about a quarter of patient. Now we have to reshape the data from a long form to a wide form, okay, from the diagnosis file, because we want to make the data much easier to look at, also easier to import into the data. To reshape the data file, we convert the single variable, the OSA or cancer, to individual variables for the OSA and the A type of cancer. So original data has only one variable indicate the patient has OSA or what kind of type of cancer. But here, this is a very long list of the variable. So that's why we kind of convert this to wide form. We create additional A variable to accommodate the information for the type of cancer and OSA. Okay. The next step, you want to see, okay, if the patient diagnosis with OSA at the baseline has worse prognosis than those without OSA at baseline. Therefore, we want to distinguish this type of patient. So we want to create a new variable called patient group. So break into three categories. The first one is OBC, meaning the diagnosis of OSA occurred before diagnosis of cancer. Next one is the CBO, that's diagnosis of cancer occurred before diagnosis of OSA. The last type is the only cancer, no OSA. So several code will be needed to be written in order to get this result and create a variable at the end of the file, as you can see here. After this process, then we're going to merge data file from this diagnosis and demographic and NACR and the vital data file. So we use a join function to connect those different files by the patient ID. So the next step is for data reduction. As we merge all those 4 different files, there are a lot of variables out there, right? 65 variables from all those 4 different files. But for a data analysis, we indeed don't need all those variables. So we just pick up, select some of those 25 variables that are relevant to the data analysis. That also can reduce the file size. Now, for the survival analysis, it's very important that, as we know, that age will influence the prognosis. So we need to create a new variable called age, okay, and diagnosis in years. So the definition of this is the time difference between the date of the diagnosis from the NACCR data file and the birth date from the demographic file. So from this one, you can see why we need to merge the two data files together, because we need to create this age. Without merge these two data files, we won't be able to create this very important age for the survival data analysis. Next step, we need to create a vital status. So the original file, the vital status code as disease or nerve. So this is the kind of categorical variable, right? However, in the data analysis downstream, we will need to create a numerical variable for these two conditions. Just because the statistical software requires this. So we just need to mutate this vital status value into a numerical value, either as 1 or 0. So that's why we're going to do this. Then the last thing that we need to do is to create variable for survival time, censoring time. Okay. So the survival times in this is the length of time between the date of diagnosis and the date of last contact that can be obtained from the NACCR data file. Also, that also need to include the vital status as 1. So we combine this two information to know the length of time and know if the patients died. Okay. The next one is the censoring time, because some patients still are alive, right, after the end of follow-up time. So we define this censoring time as the difference between the date of the diagnosis and data of the last change, okay, as well as the vital status equal to 0 based on the data format. So from here, we can generate those time, as you can see right here from the output. So all those processes and manipulation result in a final data set for the survival analysis that contain 22,100 records with unique patient 14,123 and 26 variables. As you may wonder why there are multiple records than the number of the patient here, it's because the many patients have multiple cancers. That's why there's more record than the number of the patient. So you can, with this smaller data set, you can open in Excel table to look at that if you would like to. And this is the result. As we can see here, this is the distribution of the cancer type by the patient group. Okay. You can see as here, this is the patient with cancer only without the OSA. So majority of the patient, 56% patient without OSA, and the OSA occurred before cancer is occupied only 23%. So with that, we can make a comparison of their overall survival between these three types of patient. Okay. Here we lump all the cancer type together and to look at their survival distribution over time. So here on the x-axis is the survival time after the diagnosis of cancer. On the y-axis, the survival probability. If you know of this product, we call this the Kaplan-Meier curves. So in this part, you can see this actually the survival distribution is not a different, indicated by some overlapping among the three types of patient. Now, if we look at the specific cancer, for example, look at the skin cancer, it's apparently the survival distribution is almost identical among these three types of patients, right? But if we look at this colorectal cancer, it's very clear that there's one type of patient that has much worse survival than the other two. And you can look carefully, this patient is OSA prior to cancer. So kind of support our hypothesis that a patient diagnosed with OSA at a baseline may have worse survival compared to the other two type of patient. However, this is a marginal analysis that we didn't take into account some other important factors that influence the survival distribution, for example, age. So now if we further adjust for age and gender from this Cox regression model, and then we can look at the association of the type of patient with the survival, and the end up neither of these patients associated with survival when compared with the patient diagnosed with OSA at baseline. So this is a very important issue that we need to consider when we perform data analysis by considering some of the confounding factors. So in conclusion, I would like to say obtaining the EHR data is simple. You just need to talk to health informaticians that with certain criteria and parameters, they can extract that for you. However, converting it to an analytical data set is not straightforward. It will depend on the study objective and the end, right? See how much data you will need to extract and merge and filter in. And as you can see from this simple example, that this is very complex case. And it's very time consuming. It's error prone. Indeed, I believe that the data that we create here is not perfect at all. There's still a lot of bugs that we need to deal with. And some of the code actually take a long time to finish that. For example, you want to when you reduce the very large diagnostic file down to only 3 billion records, that actually take more than 2 hours to finish that, depends on your computer power. And it's iterative, non-linear, and there's no one-size-fits-all analytical pipeline. And so don't think we can just have one simple pipeline that can be applicable to all the different data extraction and data manipulation. It requires a lot of discussion and pay attention to a lot of detail to get more accurate data. And so it's very important that we need to keep a very close communication between researchers, clinicians, health informatician, and data analysis. It's important because, for example, statistician doesn't know much about the ICD-10 code and which code should be used, right? And the research doesn't know how complicated the data analysis is. So a constant communication and back and forth to know how we can fix the bugs is very important. And that's, which is most important, that we need to keep the code, right? Once we keep the code, we will always be able to go back and see what has gone wrong, and we may be able to fix the problem. Especially when you go into the data analysis, you find something that is not consistent with what you think or your hypothesis, then you always can go back to look at the data, look at the code to see if there are some place that we have did something wrong, and that always can be fixed based on the code that we have done, and to reproduce what we want to do. So with that, finish today's presentation. I will be happy to take any question that you have. Thank you. Any question?
I have a question.
Okay.
It was few slides back when you were explaining about survival and the last call that we had with patients.
Which one?
Go back.
I mean, I can stop.
Yeah, here.
Here.
No. Go back, please.
we almost.
So there was a slide and you were explaining about their survival status, that how many days,
Mhm.
and if the status is 1 or 0 right now.
Oh, yeah. Here, right? 1 and
Mm.
0.
Yeah, and then it was written that based on the last call that we had with the patient or last visit of the patient.
Yeah,
Yeah, here.
Right.
Yeah.
Mhm.
So the date of last contact is it similar for a different patient, or like the duration of we were following the patients are similar? I mean, what we do if, for example, the following process for one patient was only 1 year, for the other one was 2 years, then we want to compare them and plot in the same graph.
That's a very good question. So, the EHR is not like a core study, right? You have very specific follow-up. So in this data set, actually we use the time from 2017 to 2022. Okay, so we have this window to decide if the patient still alive or die in the follow-up time.
Right, but not all patients joined us in 2017. So maybe one patient just joined the study in the last year or last 2 years. So then we are going to compare that their survival was shorter than the others.
You have a very good point. Exactly. That's why this is a great limitation in the EHR data, right? Because not all the patients enroll at the same time and the follow-up is different, right? And so we have to deal with this left sensor, right sensor issue in the survival data analysis.
Thank you.
Thank you. That's a very good question. So anyone ask me about how to deal with the missing data when dealing with EHR data? Okay, I would like to answer right here. Okay, missing data is very complicated. So one way you can just use available data, meaning that you use the complete data and remove any record that has missing value. But this is really problematic, right? Because you can imagine if the missing data, the variable missing the value differently from patient to patient, then once you use complete data, you're going to miss a lot of a record and end up with a very small number of patients. So it's not recommended if you have a lot of missing value. This is not an easy answer for dealing with missing data. Sure, you can impute the missing value, right? You can talk to clinician and what's the most likely value for some missing value. But when you deal with the EHR data, which normally is huge, we won't be able to impute or create those missing value data, right? So the last resort to the missing value is using the statistical technique. Statistician has developed a good methodology to deal with the missing data. Depends on the missing value mechanism. It's missing due to random or due to some special mechanism. So there's a lot of detail that we can deal with that. Sometimes we call this a multiple imputation approach or likelihood-based approach. And once you have this imputed data, then you can perform a data analysis for survival analysis. However, you can perform sensitivity analysis to compare with those with and without imputed data. Okay, if anyone has a question for me? All right, here now, and if not, I would like to thank you for your time, and feel free to contact me or our bird faculty if you need any further statistical support. And this video will be posted on the CTSI website. The slide will be posted there. Okay, thank you very much for your time. Bye-bye.
Thank you.